Yeah, so those who are trying to leave, please stay, because it's going to be fun. We're just going to show you a quick video what pop-up talks are going to be like. It's going to be about 12 talks, 5-minute talks, everything short. What's interesting is, though, people are going to share their own opinions, experiences, and their research in basically in a few minutes. So we're going to play a video.
So, how's the weather? Yeah, that's pretty much like the most boring question ever. But that's rather apt, because see, if it weren't for us humans burning fossil fuels left and right, this would actually be an incredibly boring period of time for our planet. See, Earth has seen some crazy stuff. Like there was this one time when all of Siberia got covered up in megavolcanoes and plunged our planet into a nuclear winter. And then India went and did the exact same thing just a few million years later. Or there was this other time when so much carbon was released from frozen methane deep down in the ocean, and it evaded up into the atmosphere, that it filled our atmosphere with so much carbon that it's on par with taking all of Monterey Bay, filling it with gasoline, and then lighting the whole thing on fire. Yeah, Earth has seen some crazy stuff. But the big question here is, how do you all know I didn't just make that up? First of all, I didn't. But also, if you are so inclined, you can read all about it and more in Earth's underwater libraries. Okay, these are called sediment cores. Okay, the youngest sediment is at the top, the oldest sediment is at the bottom. And written down, you can read all about Earth's climatic and geologic history. There's one caveat, though. It's not written in English. It's not written in Spanish. No, it's not written in any language that we generally speak on the day-to-day. No. Instead, it's written with chemistry, specifically the chemistry of salts. And no, I'm not talking about sodium, that common table salt. No, I'm talking those rare salts like lithium, magnesium, calcium, strontium, and barium. These 5 salts do an excellent job of tracing Earth's climatic and geologic past. But the thing is that we need to understand, in order to read this written down record, we need to know how and why they end up in the ocean in the first place. This is where my thesis research comes in here at UC Santa Cruz, because I study these 5 salts and 2 of the most crucial inputs that make your ocean salty in the first place. Specifically, rivers and groundwater. Rivers, we all know about those, right? You jump in them, you raft in them, they all eventually lead out to the ocean. Groundwater, it's a tad more cryptic. We know that we pump it out of the ground to drink, but after that, it actually does in fact flow through the sediment and leaks out into the ocean. Both of these conduits bring with it the salts of the land and translate what's happening on the land in our climate out there into the ocean, so that it's recorded for us to read about. So, in a nutshell, I study the chemistry of rivers and groundwater now, so we can better reconstruct Earth's climate in the past and improve our forecasts for Earth's climate into the future. Thank you.
All right, so these are the pop-up talks. They're short presentations about where speakers are encouraged to be as creative as they can. We're going to begin with the first one, who is Joshua Dean, and he's going to talk about, I wrote an opinion piece for a scientific journal, and it was scary as hell. So.
Everyone come up the front here so I get really intimidated, please. I want to get as nervous as possible. I've only sweat this much. I reckon I could sweat a bit more. Okay, I just wanted to start out by thanking the organizers for giving me the chance to speak here. I was especially appreciative of the fact that they did it just the other day, so I had absolutely no time to prepare this. So I've written a few notes here, but I did get a bit more time this morning when I managed to pull the fire alarm and buy an extra 30 minutes. So I want to apologize that this isn't going to be as well prepared as I would have liked. But I guess most of you have either left the room or you're looking at your phone to figure out who's talking next anyway. But what I do want to talk about is just very briefly, is about opinions in science. So everyone knows that opinions are like a-holes, and every a-hole has an opinion, but why do those a-holes get opinions in the first place? So a lot of us as scientists, what we want to do is make an opinion on, make an impact on society. We want to do something with what we do, but there's a lot of rubbish information out there that gets in the way. So for example, a lot of people don't even know that we're really causing climate change, or they might even think that the Earth is a flat disk rolling through space on the back of 5 elephants, which are in fact on another giant turtle. And that's a little bit ridiculous, but what I do tell my friends when they ask me, like, what's to do with climate change? I'm not like, well, you know, in the last work I did in the Arctic, I did some radiocarbon tracing, and it was approximately, what I found was that carbon of about 100 years old was coming out of this, and the error was 23 years, and it took me 5 years to figure out that error bar. But what it does suggest is that these systems in question are in fact in equilibrium. No, what I do is I tell them that maybe you should just have one meat-free day a week or something like that, or just use public transport a bit more, or cycle. So what I recently did is I had a crack at doing this in the scientific community as well. So ooh, it's very loud when I do that. When I wrote an opinion piece for a journal, and what I tried to do is talk about the role that I see methane playing in the future. It was me and my boss wrote this together. And we based it on several recent important studies. I did a little bit of modeling as well in this. So it was all above board, and frankly, one of the best pieces of writing I've ever done in my life, in my extremely humble opinion. But I also wasn't surprised that it got quite rapidly rejected. And that's even though that, or what they said was that they really liked the idea, but they didn't like how I did it. But it was an opinion piece for the opinion part of a journal, so I don't really know what they expected me to do otherwise. So I don't really think that we actually have enough opportunities to express our opinions. We don't have enough outlets to do this. And most of the prevailing opinions out there are those by sort of the older professors who've got a big name and a long career behind them. And let's be honest, I just know how busy those guys are. They don't have enough time to read the scientific literature. No one does anymore. There's so much stuff out there, which is why I think it's so important that we have these opinions or hypotheses or suppositions, and that we can put them out there. So I think it would be good if we could all get the opportunity to do this, to have a hand in sort of how we see the future direction of science and how we can play a role in the local community and that kind of thing. But I do see that there's an extreme irony and a white middle-class man complaining about not having enough chance to share his opinion, so I do apologize for that. So my recommendation is just put your neck out there, see what you can do, and worst case scenario is have something to rant about on a big stage like this when you don't have enough time to prepare your talk. So thank you very much.
Do we have a question for the speaker? Anybody?
No questions.
No questions. Well, next then. Thank you so much. So the next one is going to be Yahui with 3 sayings made me an isotope geochemist who studied the moon.
Slides, are they going to?
Yes, they're going to put them up. So.
Sorry, I have a slide, so maybe it needs some more minutes. And my name's Yare, so just to be clear, people call me Yaya, so you can just call me Yaya. Okay. First slide, please. Okay. Okay, so I studied the moon and then its formation. I decided to do so ever since my high school because at the moment that I heard of the hypothesis of giant impact. Ever since so, I figured out, oh, that's so cool. Our moon is the little baby of our very own planet. So there are many ways to study the formation of the moon. You can land it on the moon to leave your footprints on the moon as an astronomer. Or you can do experiments in the lab to study the rocks. Or you do simulations in your office, writing some programmings. However, I would love to land on the moon to leave my shoes on the surface. However, I don't think it is doable during my PhD program, so never mind. And I'm not really the computer science people, so I choose to be an isotope geochemist who study the moon rocks in the lab. Next slide, please. Thank you. I found 3 sayings that is really relevant and perfectly represent how an isotope geochemist behave every day. And I'll show you how it works. Please, next. The first one is the straw shows which way the wind blows. Isotopes is just like a straw. It tells us the story or what process has been involved in the past million years or billion years. I found it's really fascinating because we are able to know what actually happened in the past by measuring what is available right now. For example, a lot of isotopic systems has shown that the moon is enriched in heavier isotopes. So the moon either lost a lot of lighter isotopes during the giant impact, or it condensed only heavier isotopes during its formation. This is my motivation to do isotope. I just feel that it's so nice that we're able to tell the story of the past by measuring what we have now. Second one is start to get some tricky things. So isotope measurement is very precise, as known as tricky sometimes. The difference between few per mils can actually tell you a very, very different story. For example, not yet. Please. Yeah, thanks. So in the past, the low-resolution isotopic measurements couldn't tell the difference in terms of potassium isotopes between Moon and the Earth. However, with the high-resolution measurements that we are capable right now, it is shown that the Moon and the Earth are different in terms of potassium isotope. So the high-precision measurements of isotopes can tell us is how we differentiate different systems of different planetary body or different nature processes. So, third one, please. And then the last one is the most important one. So constant droppings wears away the storm. In my case, constant working dissolves the storm. We just have to work very, very hard day and night to dissolve the stone, to go through the column chemistry to run the isotopic measurements on the mass spec. And by doing it little by little every day, we got the very best measurements to tell the isotopic story. So even though I go to lab when the sun rises, and then I go back to home when another sun rises every day, I still love my job doing isotopes. Please, next slide. Oh, yeah, because I think geology is a science of history, that we do geology, we do geochemistry, which tells the story or the history of our Earth and other planets, which is so neat. And then I do believe isotope is where we started. Next slide, please. So like Neil Armstrong has said, there's one small step for man, one giant leap for mankind. I do believe by working little by little every day, we're able to inspire our next generation with all of the fantastic geological story, and then to inspire the curiosity of them deep in their heart to explore this wonderful universe. So I love my job as a geochemist, as an isotope geochemist to be more specific, and I study the moon. Thank you.
Thank you so much. So the next speaker is Jurai, is going to present about telling the time from a single glauconite grain, the magic of laser and gas. So a round of applause, please.
All right, it's a pleasure to be here. So over the next 5 minutes or so, I'm going to tell you, something I feel a bit passionate about recently about the geochemistry and what are the potential next avenues for the geochemical research. So can I get the slide on? Just one slide.
Slide up, please.
Okay, maybe I'll start.
Awkward silence.
There.
No, that's not.
That's not the right one.
Let me go and check. It's the previous one.
It's the slide with name GAURAJ.
You don't have it?
No, it was uploaded there.
So it's the Farkas. Yeah, Farkas. Yeah, Farkas. This one. This one, yeah. I couldn't hear. Okay, go. Yeah, it's fine.
All right.
Here you go.
So there it is. Okay, so I'll start here. So basically, what I'm going to share with you today is some, potentially new, exciting research we doing now in University of Adelaide, and in a non-scientific way. So this is, in a way, joint research between University of Adelaide and colleagues at Indian Institute of Science and University of Gothenburg, and basically. The idea is there, to use glauconites, which is a rare mineral, in sediments to date that. So, I'm not a geochronologist, so as you can see, the title said telling the time. So it's basically talking about the geochronology. But my background is a low temperatures isotope geochemist, and when I moved to Australia a few years ago, I realized the bread and butter of geochemistry there is geochronology. So in a way, to be taken a bit more seriously there, I realized I have to do a bit of geochronology there. And by serendipity of events, we acquired one instrument, which is called a collision cell mass spectrometer, which allows us to date the minerals in non-traditional way. So I'm just going to illustrate it a little bit. So normally, if you want to do the rubidium-strontium dating, can I get a first click on the slide? Yeah, so that's his illustration here. So as a geochemist, traditional way, you want to do rubidium-strontium dating, you separate rubidium, which is your green apple, from strontium, which is your red apple, but you have to do it in the clean lab. So it doesn't allow you to analyze samples with laser. So what this new instrument allows you to actually separate these two apples or two isotopes in the instrument. And if you can do that, then you can basically separate these elements online, and you can then date individual minerals with laser. So that's shown there, that you can, from a single glauconite grain, which is about 0.5 millimeter big, you can basically put few spots through that mineral. Can I get the next slide? And
you have a
next click.
You have a clicker already.
Yeah. And what you get is basically the age. So by this means, you can get age of the mineral, which is 1.64 billion years. So in a way, this is a new way how you can start dating minerals with laser. And how the system works, just last minute, is we have a collision cell, and basically rubidium you have the cell filled with oxygen, so this will be oxygen, and rubidium will fly through that cell, and you can measure it at rubidium-87, but strontium is very friendly with the oxygen, so it will combine, and you measure these as strontium with different mass. So this way, we can separate these two isotopes and get the age what we need. So I'm sure we'll be seeing more of this research in the future in Goldschmidt, and I think I'll finish that. Thank you.
Thank you so much. So we're going to have the next speaker, who is Rose Jones. Is going to be talking about mining the deep sea floor. A round of applause for Rose as well. You have a clicker there as well.
All right, everyone hear me? All right, so I'm a deep sea microbiologist, but I used to be a mine waste microbiologist. So mining the deep sea has me coming and going. So how often do you think about the deep sea? Even to those of us who think about it all the time, it can seem as remote and as alien as space. Because after all, we know more about the surface of Mars than we do about the surface of the deep sea. And more people have been to space than to the bottom of the sea. But each and every one of us has a connection to the deep sea in our pockets right now, which are these. We're using more rechargeable batteries for phones, laptops, electric cars. And these have rare metals in them, like lithium, cobalt, and magnesium. But these are rare. There's only a few mines in the world that can produce these metals, but the demand is going up. So we're turning to the deep sea to try and bring in the shortfall. So there are companies developing this technology right now, and they're making these tough, impressive remote-operated robots that can go down and scrape off like the crust of the sea floor, or hoover up manganese nodules, or dig up the hydrothermal vents to get at the ores. And the idea is this waste rock is then piped up to a ship that sat miles or kilometers, depending, if you're on the sea surface. And then the waste rock and the treatment chemicals are then dropped back over the side, and they're dropped into a plume which enters the sea. And even though this sounds very technical, the basics are similar to mining on land. And see, this is where perhaps we ought to stop and think a minute, because mining on land creates a whole load of problems like noise, dust, release of heavy metals into the environment. And these problems persist for hundreds of years on land, and they're neither cheap nor easy to clean up. And the laws of chemistry and physics being universal, these problems are probably going to crop up in the deep sea mining as well. But because we know so very little about what's going on in the deep sea, this is a big problem, because we don't know how it's going to affect it. We don't know which parts of the deep sea have important endemic wildlife. We don't know which hydrothermal vents have a microbial community that might give us clues to life on Earth or even out in space. And these environments have been left undisturbed for thousands of years, so we really have no idea how they're going to react to being disturbed. And there's one of the few studies on the subject showed that after 35 years, a disturbed patch of seabed, there was no recovery. It looked exactly like it had when it was mined. So what can we do? Well, we have a couple of options. We can do nothing and say, yeah, it doesn't matter, we're never going to see it, it's so far removed from us, who cares? Or we can say, yeah, all right, it's having our phones and laptops and what have you, and mining the seafloor will be an inevitable consequence of our need for modern technology. And we would just say, okay, well, we'll just go to the less important parts. But how do you define less important? And who gets to choose? Who gets to make that decision? This approach would need an awful lot more research, legislation, and a ton of enforcement to actually work. And the third option is we can say, no, it's not worth it, we'll not go there. But in order for that to work, we've got to work really hard on reducing the amount of our demand. So we need to do way more on recycling electronics and making them last longer. But the thing is that this technology and this industry is starting up right now. The rules are being written literally. I think there was like 2 weeks back, there was a big thing about it. But yeah, so whatever you think, if you get your opinions known now, you might have a real impact on how this technology develops. Thank you.
Thank you so much. So the next speaker is Tintin, who's going to present about cable bacteria, a wire-like bacteria that transports electrons over long distance in sediment.
Thank you very much. Yeah, so I'm wondering, like, any of you have ever had a problem of, like, you need really important phone call, you're waiting for that, but your battery is dead, or you really need to charge it, but you don't have the cable, Or sometimes, I have to buy once or twice because my charging cables for laptops and computers and like cell phones, because they're broken. And every time when that happens, I'm just like, can we just make these wires and all these, electronic devices like more portable? Especially, we are so heavily rely on the electronics nowadays. So can we make these wires thinner, lighter, or even it would be best if they can fix themselves when they're broken? And can we do that? Not yet, but there's a hope. And this hope doesn't come from any fancy labs from these technology companies, but they're really from this seeking muddy Danish sediment. So next slide. Yeah, so I will not explain it too much about that, but for a long time, people have been puzzled by the geochemical profiles in this Danish sediment because the only hypothesis they can make of to explain the whole profiles of oxygen, sulfide, and pH is the oxidation of sulfide to sulfate. So this redox reaction can happen not really in one place, but it's separated into two half reactions, and one is happening on the surface of the sediment, and the other half reaction is happening several centimeters down in the sulfidic deep sediment. So that sounds great. Sounds like we have a sediment battery out there, but the problem is we never find what the batteries are, or how this battery can really transport these electrons generated by oxidizing sulfide to the top, reduce the oxygen. But for a long time, people were searching for minerals and so on. But there's one day. Next slide, please.
Yeah, you also have a clicker.
Oh, clicker. Oh, cool. So it's there's one of the scientists just all by sudden and he say, why not I just took a piece of the sediment, and then he cracked open the sediment, and all by sudden the light was right on the exact right angle, and he saw a lot of filaments inside this sediment. So what are they? And so next, how can I click on that? I don't know. Okay, so next slide. So he found these filaments are really, they're moving, they were like gliding, they look like cyanobacteria, but they were not green, so they were not cyanos. They're kind of new type of bacteria. So what are they? Are they be our batteries, or can they really long enough? Because it's several centimeters in the between, right? And in fact, this new bacteria, they can really grow up to several centimeters long. I can pick up from 5 centimeter long filaments. So the distance was not the problem, and also they're quite dense. So from 1 square centimeter of sediment, this total length of these filaments can be more than 2 kilometers. And how can we prove that they are transporting electrons? If we cut off these cables, or I'm not saying, cut off these filaments, so the previous electron potential that existed in the sediment will just be gone. So that's a big, strong evidence, and we also had other tests. So there's a big chance that we got this battery in the sediment. So next, please. And if we closely look into the structure, the surface structure has very unique, this long string-like morphology. So people believe that electrons are transported through each individual strings. And next, please. And there's one thing I want to mention. So this is a cross-section of this bacteria. And then we see these ridges around, they're the strings. And one thing very interesting is the string numbers is always like 13, 15, or 51, those odd numbers, which are not very commonly seen in nature, in organisms. So I think the next videos is gonna explain more and better than I do. So why not we just see the next video? So if you click on that, So my colleague just did a very good experiment. So he put like the incubation chambers. So one of them was fitted in like sulfidic sediment with cables, and the other one was just flushed in with oxygen, and there was a channels together. So he saw there's a fast moving and growing of these cable bacteria, and there's a lot of them. And they always trying to reach out their food, and there are also competitions. You can see some of them, they will just break on each other if they just all of a sudden cross on each other, but they're not dead. They're still trying to going back to the right position. And they always move with lasso top, like head, and trying to reach out the sulfide oxygen that they need. And they're really growing fast, and they're smart, in fact. They find the shortest carts where they can reach their food. And with that, I'll just finish my talk.
Thank you so much. So the next speaker is Marlies, and she's going to talk about the cultural side to mine rehabilitation in New Zealand. There's a clicker there as well, if you can find it.
Hello everyone, my name's Marlies. I'm a PhD student at the University of Canterbury in New Zealand. So today I want to share with you my journey of discovering how the cultural aspects of mine rehabilitation are taken into consideration in New Zealand, and also the story of a tribe or an iwi that my research group has partnered with to carry out this mine rehabilitation work. So in New Zealand, our country is founded on a treaty signed between the Indigenous people group, who are the Māori people, and the British settlers. So the Māori people, they are the tangata whenua, they're the people of the land, whereas the settlers, they are tangata tiriti, which is the people of the treaty. Now for the Māori people, being tangata whenua, the people of the land, they have this really deep connection to the land. So the land is part of their ancestors, and along with that, the resources are like a part of their ancestors. They're connected to there's no distinguishing between the resources being extracted and like their ancestors. So in this image, this is like exactly what the area where this particular mine and the people they live. And you might also be able to see that the mountain has a face looking skyward. So for these people, the mine which was in the mountains above their town, it had scarred their mountain, and the toxic acid mine drainage was leaching into the streams, and the streams could no longer support a healthy ecosystem. So for these people, their mana, which is the prestige, the respect that they are due, their self-worth, being connected to the land, the mana had been brought down, been degraded, along with the mountain being degraded. And the modi, which is the life force of the stream, that's also been degraded. So it had been brought down from modi ora, which is a life-supporting, life-enhancing life force, down to modi mata, which is a dead stream. So for them, like when I entered this story, I heard their distress at the mana of their mountain being degraded and the modi, the life force of their stream, being degraded. But I also heard of this restoration project that had taken place. So the limestone had been added to the mine tailings and adits to halt the generation of acid mine drainage, and the tailings dam had been revegetated and grassed over and planted. So they had this hope that once the acid mine drainage stopped flowing into their streams, then the streams would be able to recover, and the forest would grow back over the mine, and it would just kind of like fade back into the background and what had been there previously. So yeah, so when I visited them, yeah, I just grabbed onto that story. It was just like hearing like where they had been, where they'd come from, and also like looking to the future. So the restoration project, it had reached the restoration targets of the local governing authority, which meant that the stream was safe for contact recreation, but that didn't go far enough to restoring the whole ecosystem of the stream. So these people, they were quite disappointed. But with this research group, we were working with them, partnering with them to be able to do even more restoration work there, and to be able to have that ecosystem restored back into their streams. So they had formerly, like, eels were living in their stream, and that was their food source. And so because of the acid mine drainage that had been leaching into the streams, the eels were no longer suitable, and through the restoration, they had this hope that the eels would return to their stream, and they understood that it wasn't just going to be a 2-year or a 5-year project, but this was for their grandchildren, their great-grandchildren, and if they could pass on that vision of where they were going to get to and having the eels and their food source back in their stream, then they could be proud, and they could, uphold their mana. And through my PhD research and my future career, I hope to be able to do all that I can do to be able to help them to realise that goal. And then my mana will be, brought up. So, yeah, and I just want to say a massive thank you to my supervisors who have got me here, the iwi liaison group, the Māori people who are living in this area, and two awesome ladies, Jo and Robin, who they just paved the way for this race relationship, and have been, they literally wrote the book on how mine managers can engage with iwi in New Zealand. So, thank you.
Thank you so much. So the next one is going to be by Yan Zhen, and the title is, Why Do Americans Knowingly Drink Poisonous Water? Yes, sure. There's a clicker here. It's supposed to be this one. If not, you can just announce it. There's supposed to be one.
So, in the pointer.
Just use the microphone and you just tell them, and they'll switch.
All right. Hello, everyone. It's maybe half of you are the speakers, and I feel like I'm the only old person who popped up. My name is Yan Zhen. I'm a geochemist, and I became a professor at SUSTEC in China in 2016 after spending 18 years on the faculty of CUNY and as research scientist at Columbia. So this talk is about 43 million, mostly rural Americans who rely on domestic wells for their water supply. And you may or may not know, the Safe Drinking Water Act that covers unionized water safety does not really apply for these domestic wells. So this means that these 43 million Americans or 50 million households are responsible for their own water safety. And in New England and in New Jersey, such wells are very often drilled into the bedrocks, and then very often they contain arsenic-rich pyrites, and they poison the water if it is not treated properly. So in this, can you do the next click? So in our great nation of unbound optimism and the birthplace of Google, this is the short answer to this question, and then I'll explain. Next. So why should anyone care about arsenic? Arsenic has been known as the king of the poison and the poison of the king. Inorganic arsenic kills people slowly by inducing a range of cancers, cardiovascular diseases, etc. It can also make people, especially children, dumber, as it is known as neurotoxin. Geogenic arsenic has been detected in groundwater at levels unsafe for human consumption in more than 70 countries, slowly poisoning over 100 million people. In the US, recently Joe Ayo of USGS estimated that 2.1 million domestic well users are exposed to above the MCL levels of arsenic. Of course, there are a lot of uncertainties in this estimate because not many domestic wells in this USGS data set have been, there just aren't that many. And of the few thousands, about 10% is above the MCL. Fortunately, where we have a lot of arsenic, such as the American West, there aren't that many people. So overall, there's only about 2.1 million people, not 4.3. So I will mostly, click please, describe the findings of my group in Maine and New Jersey next. So next please. I wanted to highlight the behavioral vulnerability among the domestic well populations. So I studied arsenic in Bangladesh also for many years. And when I give talks and after my presentation, very often someone will ask, why don't they do something about their arsenic? So those seemingly very naive questions actually led me to health behavior studies that really was very intriguing. Click, please. So this includes a classic by Rutgers University psychology professor Weinstein, who really documented this optimistic bias phenomenon. Basically, we believe we are better off than our neighbors. So in other words, humans have a tendency to believe that we are not only better than average, we are also better off than average. Next. So former graduate student Sarah Flanagan mailed survey questionnaires to more than 1,000 randomly selected private well households in Maine and New Jersey. These red dots indicate the households responded to our survey. And based on, and you can see underneath these grids are 2 by 2. They are percentage of arsenic above MCL, and in some grids, the darkest are about 40%. So we do have a lot of people in these regions exposed to arsenic. Next slide. So there are several lines of evidence suggest that for optimistic bias. First, in both states, less than half of households have actually tested their water for arsenic. Maine is 44%, New Jersey is only 40%. Second, of those who have tested and are treating their water, again, less than half have tested their treated water for arsenic, so they just trust their treatment system. And then finally, when we followed up on a population, we have tested their well water by yet another former graduate student, Chang Yang, and we send them the results and brochures telling them what to do. More than a quarter did nothing. So this is what I mean by knowingly drink poisonous water. So next slide. So to protect health, we have come to this position where we believe that every domestic well should be tested for its water quality at least once, preferably regularly. And the question is how and who pays. Our study has found, for example, in New Jersey, the testing law is really good at getting some people to act. So more testing laws like these ones in those 5 states are going to be helpful, and I'll be happy to send you these papers. Next slide. So please email me with any questions if you're interested in arsenic or jobs or interested in contributing to the session that I'll be organizing next year. Thank you very much.
Thank you so much. So the next speaker is going to be Jeanette about basically, well, we changed it a little bit, right? But the pollution in the Indus Basin in Pakistan.
Hi, hello everybody. I'm lucky that just before my presentation, the professor was presented her, and she is also working on the similar lines. And so she mentioned that the Americans are knowingly drinking the water, but we are so unfortunate that we unknowingly we are drinking the water in our country. They don't know the status of their wells. And I just came to know here, they first test their well and then they go for it. And our people are so unfortunate that they even don't know what's the status of their well and they are drinking. So we are currently working on the groundwater geogenic contaminants in the Indus Basin. You can see in the map, this shows the major, and this is considered as the world most like productive aquifers, being drained by the 5 major rivers from the Himalayas. You can see the blue lines as rivers, and each pie diagram shows an individual village. These are 200 villages, and those were tested from 2014 to 2018. It was a joint project by United States and our Higher Education Commission. So you can see that how widespread the contaminant is. The red color shows dangerous, and even it's in most of the regions which are affected, you can see that it's even at poisonous levels. Next, please. There's a video clip. I can show you what it does to the local people. This is crippling fluorosis, and like hundreds of children are affected, and unfortunately they even don't know that from where this disease is coming. And there was a child, this was the child. When I visited his home, I asked his parents, do you know have you ever been to a doctor? He said that we went to a doctor and he gave him the medicines of TB. And now finally he is suffering from TB too. So this is so unfortunate due to the lack of education and lack of poverty. Next please, there are hundreds of people who are suffering from dental and skeletal crippling fluorosis, but they don't know. As the professor earlier mentioned, that the US people are drinking knowingly, but we are so unfortunate that they are unknowingly. So what is interesting about this? Next please. So there are some simple things which why we are not doing. We found it in our blanket testing surveys. What is a blanket testing survey? Next please, I will show it here. This is a blanket testing survey. In the blanket testing survey, when you visit an area, you test each and every well. We don't leave any well untested. It helps us in finding that this is the most contaminated part of our basin, and even in the most contaminated part, we found some very safe wells, like less than. And this is very interesting. Like people don't need to do anything. They just need to switch from the unsafe wells, which is few meters away from them, to the safe wells. So this is how we are reducing the exposures. And what we did, interestingly, we visited those villages which were highly affected after our testing campaign. And we found that 70% of the people switched from the unsafe wells to the safe wells. And this is helping us, and we are now promoting this kind of studies because a lot of areas is still to be tested. And this testing campaign can help us in finding the safe aquifers, because all of the wells are not contaminated. But here, what I am working on in my PhD project is, this is very interesting, that why within the same vicinity, within the few meters, even there were 2 wells in a single house. One was highly contaminated and one was not, and they were very much close to each other. So this is not known why it is so much heterogeneous. This is something scientific which I am not presenting here, but this is something interesting which I wanted to show you, that we have the opportunities to provide the safe water to the people, but just by blanket testing. Okay, thanks.
Thank you so much for sharing. So Nicola is the next one, and is going to present about Back in Black.
Hey, thanks. Just like the first speaker, I'm a little less organized than I'd like to be, because I decided at the last minute to talk about something different than my research. So I just wanted to say my name is Nicola, and I love coal. I love coal so much, I do it as my job. And it's not very hard for me to admit that to you guys, because that I'm a coal geologist and we're all geochemists here. But if I walked downstairs and just outside onto the street and started telling people I love coal, I might get a bit of a different reaction. And I don't think it's very hard to understand this and understand why, because even in North America, Australia, depending on where you live, coal has a very black reputation. So for most people, when they think about coal, they think about these sort of toxic black lumps that we either burn to make steel, or even worse, we crush them up and we put them in a power station to generate energy. So when we think about coal, often we just think about coal with its association with modern climate change, which isn't wrong, not at all. But this is the perception that most people have of coal. And that is the most true, I think, for where I'm from, which is Australia. So in Australia, we have a very deeply enriched mining culture, particularly coal mining, that contributes a lot to our economy. The only thing is last year the National Bureau of Science, CSIRO, in Australia did a study, and they found that most of the people in Australia thought that the mining industry was the least trustworthy industry in the entire country. So it was a little baffling for some people to know that, given how much Australians rely on the mining industry. So coming from there, something else is that in Australia, we actually burn coal for energy. 75% of the energy we use comes from burning coal in power stations. And yet, Australia has one of the largest and widespread grassroots movements and movements against the coal industry and the mining industry in the world. And again, rightfully so, there's no reason this shouldn't exist. But the problem is that that's also working against things like coal research, or working in areas where we're somehow with or adjacent to mining companies. So that leads people to believe that if we can't trust a mining company because of their practices, we can't trust researchers or scientists who are also working in this field. So that becomes a problem for us as scientists. So, and this isn't a problem exclusively for coal. I'm talking about coal because I'm a coal geologist. But if you're working in oil and gas, or if you're working in iron ore, you're working in base metals, anything like this, you might find that it's very, very difficult to communicate your research to the general public, because you have to work against this reputation that the mining industry has sort of set in front of you. So it becomes very, very difficult, because inadvertently the people we're trying to communicate to are the people who are often paying for the research, or in part paying for our research. So it's up to us to sort of try and communicate that to them. And so that's something we need to get over as geochemists. So I think for a lot of us, what we do is when we talk to people out in public, we often make provisos. So for instance, for me, I'll say, oh, I work in coal, but I work in coal as like a fossil to study ancient environments. I don't burn it or anything like that. Or I might say, yeah, I get all my samples from mines or from drill core, but I don't do anything to do with mining. And the problem is that when we add these provisos to our work, we're inadvertently, and not meaning to, not being totally honest with people. And that becomes a problem, because then we're just reinforcing this idea that the scientists adjacent to mining or working with mining companies can't be trusted. So we need to really get over this tendency we have to add provisos to our work. So the problem is that when we want to be honest and say everything about our research, our world becomes very, very small. So it's limited to things like the Heinz Convention Center, and even then, so of the 4,000 people here, maybe only 1,000 will understand your research, maybe only 500, of those people will understand where you're coming from when you're trying to communicate. So what we need to do is overcome that barrier, not only within our own field, but to the general public as well. And the answer is like, how do we fix that? And I don't have an answer. But I think one of the main things we need to try and do is to start dialogue. If you're working in industry or adjacent to industry, start creating dialogue between yourself and people like in this picture that we have up here. So this is from an anti-coal protest in Sydney, Australia, which had about 8,000 people. That happened only recently. So we need to be able to start dialogue with people who may or may not know what you do, that may or may not be within the industry itself. So, and that becomes very important because when we are able to give our opinions to different people, they're able to respect and give you credit for something. So instead of having, like reinforcing this negative opinion that people have of the mining industry, you want to create a positive opinion for people who are working in science. So whether that's from just once a year doing a talk at a local pub, or you have a Twitter, you're starting a blog, just doing something where you're able to give yourself a platform to give a meaningful message to a non-scientific community. And I think that's really important for us as individuals as well, because it allows us to get out of this bubble, basically, that we trap ourselves in, where we're in these echo chambers, where we're only talking to other scientists. So for me, it becomes incredibly important because I think we need to be able to convince the general public and the voters why we do is important, why it's important, so they can vote and they can convince the government why they think that's important. And ultimately, they're the people who give us our jobs. And without them, we're just scientists who have this bad reputation, as dark as the rocks that we work on. Thank you.
Thank you so much. The next is Gabriella, and is going to present about Leave No Coal Stone Unturned, about the PhD thesis of a hydrologist becoming a geochemist.
Good afternoon, everybody. I'm so happy that my previous speaker told you something about coal. I also love coal, but from a different perspective. So, how many of you wondered about your feelings for science? Or how many of you identify with the typology of scientists fighting all the weapons to obtain something from an experiment? And the answer is simple. I think most of us here feel the same way. Why? Because science gives us a profession not like any others, where it allows you to work, let's say, for 8 hours a day, and then for the remaining 16 hours, you can enjoy life with friends, family, and your hobbies. No, life of a scientist is not like that. It haunts you, it overwhelms you, and once you catch the bug of science, it will never let you go. But like a German painter once said, the artist's arm is his feeling. So the feeling is the law of an artist. And I can extend this for the scientist as well. In my case, as an early career researcher, currently under the process of completing my PhD, my work is under the spectrum of what I call scientific romanticism, because I can feel the same kind of emotions and feelings like an artist when I'm discovering something, when I ask myself a question, a scientific question, when I'm reading something, or even when I'm getting inspired by a professor's talk. But then I'm only hydrologist, so maybe you are asking me, why is a hydrologist doing, what is a hydrologist doing here among so many geochemists? Well, my story goes like that. I will take you shortly to my PhD story. So, geochemistry first appeared in my radar as just a passion in the high school when I used to participate in earth sciences competitions. By then, I started to love more and more earth sciences. And then I decided to take my bachelor in geomorphology, and then I did my master in hydrology. Then I could say I'm a romantic person, right? At least in the scientific part, sense of the idea. Because I simply did everything from passion for the earth sciences in general. But then, when I started PhD, everything catapulted me in the realm of chemistry. By the way, subject that I loved at school, but I ignored. So I started my PhD just following a personal proposal of the project, just by a simple curiosity of studying the hydrosedimentary dynamics of a river basin in my home country, Romania. And by that time, my Romanian supervisor and I were aware that actually my thesis will not be something very special, just a typical hydrology thesis, without many technical details, because we didn't have the financial means to do something, let's say, out of the ordinary. But still, in my despair, I started to search challenges, to search international cooperations, just to carry out my project. In the end, I signed a PhD joint supervision with my second coordinator from France, and then I started my real PhD adventure park. Why I'm saying that? Because enthusiastically, I thought that having two hydrology supervisors, expert in hydrosedimentary dynamics, on my side, I will manage to grasp all the statistics behind hydrology. I will manage to adapt or to replicate a fancy hydrological model, and I will really manage to find the sources of the fine sediments in my watershed. But in fact, the reality was nothing like that. I simply got stuck in my methodology, I got hampered by the lack of hydrological data, and I simply felt that frustration of not actually contributing with anything new during my PhD thesis. Everything until one day, when being on a field trip, I just noticed that the fine sediments in a riverbed deposits contain various quantities of coal. And then I asked myself, why not using coal as a hydrosedimentary tracer? So in this way, coal practically saved my thesis and myself. So without a previous lead, we just started to look for an accumulation riverbank, just downstream all the possible hydrosedimentary sources, to find deposits of fine sediments left by the most recent floods. And wow, what we discovered. So beautiful layers. Some of them were darker, meaning that they had more coal of two different species. Some others were simply lighter, grainy, and more granular. This meant for us that actually our sediment layers came from different sources of the watershed. So then I started to actually search methods to analyze this coal content and the associated rare minerals from the sediments of my watershed. And then I started to ask myself, who thought that in the 21st century, when coal is practically widely seen as a major culprit against behind global warming, it will actually mean for me an excellent tracer for my river dynamics. But now, my takeaway for you is not literally what my title said, and not even this funny resuming picture of my thesis. No. What I want to transmit, the general message behind every idea I just mentioned, is for the early career researchers and for every PhD student. Just go to the end of the road and don't let you fall. So even if you don't have a lead, and even if you don't have methodology at the beginning or even financial means, just go to the end and find a solution. You might not get the financial satisfactions or scientific distinctions at first. That was in my case. So in order to find methodology to analyze the hydrosedimentary dynamics, I had to knock at the doors, to look left and right for help. And sometimes I saw some doors open. I entered, but some of them just closed then. Some professors I asked for help just asked me, why are you using geochemistry and organic petrology? Because your thesis is essentially in hydrology. What else do you want to prove? Because it's so simple. River is transporting sediments all the way from upstream to downstream. It's the gravitation and the slope. What else do you want to prove? But still, I continued searching, and then I found collaboration outside the university I'm actually working in. So in the end, the core of my PhD thesis is not anymore of hydrological nature, but more of geochemical nature. But now, also modestly, I will ask you a final question. Do you think I'm becoming enough of a geochemist to stay here in front of you? Thank you very much.
Yes. Thank you so much for sharing. The last speaker is going to be Simon Meaton, and the talk is Why Am I Passionate About the History of Deep Carbon Science and the Great Pioneers Who Pushed the Frontiers of Geoscience to Reveal the Complexity of Earth's Inner Systems.
First of all, let me explain to you that when it comes to geochemistry, I am an early career scientist. My PhD is in astrophysics, and I worked in astrophysics and cosmology for several years before joining Cambridge University Press as the Director of Science Publishing. And I ran the Science Publishing department of the press for 22 years, and then I decided to take early retirement and switch to becoming a historian of science. And I'm early career because my fellowship of the Royal Historical Society, which is the professional qualification in the UK, was only awarded 2 years ago. So, deep carbon science, or the history of geochemistry and geophysics of the Earth's interior, there is very little material at book length on this subject, and I became passionate about it because I've found that writing history and talking about history is a very good way of extending the outreach of a subject and communicating with the public, communicating with your friends and your family about what it is that you are working on. Now, a history of carbon science, we've already had 2 carbon talks this afternoon. It's the 4th most abundant element in the universe, and in writing about the history of carbon in the Earth, we actually start in the very early universe, explaining how the chemical elements were forged in the interiors of stars. And that's a very good way of actually beginning to engage people's interest. In writing about history, I am very keen on writing about people rather than dates. And obviously, in the history of science, you're not writing about battles, or thank God, you're not writing about politics. Deep carbon, which is the expression used by the Deep Carbon Observatory, is carbon that is not in the atmosphere, nor the carbon that's in the oceans, and it's not the carbon that's on the surface. So it's all the carbon that is below the surface. And there's a surprising amount of this. For example, the deep biomass, the microbial life below the surface, the total amount of that is a few % of the amount of biomass which we actually find at the surface. Other reasons why it's very interesting to work on deep carbon is take diamond, for example. Diamond is formed under conditions of very high temperature and very high pressure. The diamonds that actually reach the surface are 750 million years old, and they contain inclusions, and by examining those inclusions we can learn all about the temperature history of the diamond, and we can make profiles and histories of the history of the temperature of the mantle and so on. So there are very sort of interesting intellectual puzzles. And it's because carbon is so abundant in the universe, and yet we do not know very much about what the carbon in the Earth's interior is doing. And so that's why the Deep Carbon Observatory, which is a consortium of more than 1,000 professionals in physics, chemistry, biology, geology, oceanography, and so on, was founded in 2009 in order to increase collaborative work. And I was engaged as a historian to document the work on carbon in the Earth's interior that had taken place before 2009. Now, why I think it's worthwhile taking an interest in the history of science is if you look into the history of the areas that you work on and people who worked on it in the past, you can learn quite a lot about the scientific method. You can also learn about the mistakes people make. One example I like to give of this is scientists who spend too long working in the field and on the intellectual problem, which they did for their PhD and their postdoc, or for their first career in tenure. If you've read the biographies of as many scientists as I have, it is very evident that it is much more common for a high productivity, high achieving scientist to work on several problems in succession than always stick at the same problem. In the history, we also come across remarkable people. Victor Goldschmidt, for example, he was within a few seconds of being put on a train as part of the Holocaust when he managed to escape. And after escaping, he was then rescued by British intelligence and taken to England because it was felt that with his knowledge of geochemistry, he could contribute to the war effort and so on. And then lastly, in doing the history, I have found it fascinating to work on some of the long-run problems that took a long time to solve. The age of the Earth, the question of does the Earth have an internal heat source, and the issue of continental drift. All three of these were intellectual puzzles that lasted for almost or longer than a century. And it's working on the people and working on the puzzles and the history that I found really enjoyable. And I hope I may have stimulated some of you to take more of an interest in history. It's very easy to do with the Wikipedia. Thank you very much.
Thank you so much. So before we all run to the sessions, we have gifts for participants. And we have gifts for every participant, right? But we have 3 particular ones for the most impacting presentations. So I would like you to vote based on, you know, exactly. So just yes, exactly. Speaker allowed to vote as well. So basically, just let's vote for the first one. Just raise your hand if it really impacted you in a way. If you remember it, if wasn't really memorable, then, well, so, okay, 0. Or not here. So maybe people here didn't see it. So the second one is 3 saints that made me an isotope geochemist who studied the moon. Does anybody remember that one? Okay. Do you? Yeah. Okay. So then telling the time from a single glauconite grain, the magic of laser and gas. Does anybody remember that specifically? Somebody raise their hands? No. Okay. So mining the deep sea floor, Rose Jones. Okay, we have 2, 3. Oh, 1, 2. Again, can you do it again? 1, 2, 3, 4, 5. 4, 5, right? Cable bacteria, a wire-like bacteria that transports electrons over the long distance. Wasn't impactful? 1, 2, 3. 1, 2, 3, 4, 5, 6. Okay. Cultural side to mine rehabilitation in New Zealand. Impactful or not? Yeah. Okay. Why do Americans knowingly drink poisonous water? 1, 2, 3, 4. Okay. Full redistribution aquifers, the Indus Basin and Pakistan. 1, 2, 3, 4, 5, 6. Okay, 7. Got it. Back in black. 1, 2, 3, 4, 7. Well, I mean, yeah, you don't need it. Leave no cold stone unturned about the PhD thesis of hydrologist becoming a geochemist. Okay, 1, 2, 3, 4, 5. Okay. And the last one, why am I passionate about the history of deep carbon science? Okay, 1, 2, 3, 4. Okay. So, we have 2. So basically, Pakistan, Indus Basin got 7. Back in black got 7 as well. And the cable bacteria, awara-like bacteria, is the 3rd place, basically. So we're not going to choose who is the first, who's the second. If you want, we can do it. But it's basically the first 3 are getting gifts from the sponsors that we have. And everybody else are gonna, can you guys come up and we're gonna give you, for basically it's a Klein Mineral Society extends you 1 year membership in their society. So just come up and do that. Also, the videos are recorded professionally. So basically, we're going to share the videos with you. It's a shame that we had less people in the end, but you know, the alarm and all that. Next year, we'll make sure that we fill this up. And so yeah, come up here and applause each other. And
I forget which is the winner. Who else is the winner? Who else won?
Oh, I'll do it.
Did you win?
Apparently.